What is label propagation and what are its use cases? A. It is a supervised learning algorithm that uses labeled data to predict unlabeled data. B. It is a semi-supervised learning algorithm that uses a small amount of labeled data and a large amount of unlabeled data to predict labels for the unlabeled data. C. It is an unsupervised learning algorithm that uses only unlabeled data to discover patterns and structure. D. All of the above. A. It is a supervised learning algorithm that uses labeled data to predict unlabeled data. This statement is incorrect. Label propagation is not a supervised learning algorithm. Supervised learning algorithms require fully labeled data for training, while label propagation leverages both labeled and unlabeled data. A. It is a supervised learning algorithm that uses labeled data to predict unlabeled data. B. It is a semi-supervised learning algorithm that uses a small amount of labeled data and a large amount of unlabeled data to predict labels for the unlabeled data. This statement is correct and accurately describes label propagation. It operates in a semi-supervised learning setting, utilizing a limited amount of labeled data along with a larger set of unlabeled data to predict labels for the unlabeled data. B. It is a semi-supervised learning algorithm that uses a small amount of labeled data and a large amount of unlabeled data to predict labels for the unlabeled data. C. It is an unsupervised learning algorithm that uses only unlabeled data to discover patterns and structure. This statement is incorrect. Unsupervised learning algorithms work solely with unlabeled data. Label propagation, however, relies on a combination of labeled and unlabeled data, making it a semi-supervised approach. C. It is an unsupervised learning algorithm that uses only unlabeled data to discover patterns and structure. D. All of the above. This statement is incorrect. As only option B is correct, this option is incorrect. D. All of the above. B. It is a semi-supervised learning algorithm that uses a small amount of labeled data and a large amount of unlabeled data to predict labels for the unlabeled data. Semi-supervised learning. A learning paradigm where the model is trained on a combination of labeled and unlabeled data. This approach is valuable when obtaining fully labeled data is expensive or time-consuming. Semi-supervised learning algorithms leverage the information from both labeled and unlabeled data to improve their performance. Image classification with limited labeled data. In scenarios where labeling images is costly, semi-supervised learning allows you to train models with a smaller labeled dataset, using the unlabeled data for better generalization. Text categorization with unstructured data. Text classification tasks can be challenging due to the vast amount of unstructured text data. Semi-supervised learning helps categorize text documents with limited labeled examples by learning from unlabeled data. Semi-supervised learning. A learning paradigm where the model is trained on a combination of labeled and unlabeled data. Label propagation. A specific semi-supervised learning algorithm that propagates labels from known data points to their neighbors based on similarity. It operates by constructing a graph representation of the data, where nodes represent data points and edges represent relationships between them. Labels are then propagated across this graph, effectively spreading the information from labeled data to unlabeled data points. Customer segmentation with limited profile data. When you have limited customer profile information, label propagation can segment customers into distinct groups based on their purchase history or behavior by leveraging a small amount of labeled customer profiles. Social network analysis. Label propagation can be applied to social networks to identify communities or clusters of users based on their interactions and connections. This can be useful for targeted marketing or understanding user behavior. Label propagation. A specific semi-supervised learning algorithm that propagates labels from known data points to their neighbors based on similarity. Graph-based learning. A framework for learning from data represented as graphs. In graph-based learning, data points are treated as nodes in a graph, and their relationships are represented by edges. This approach allows for capturing complex relationships between data points, leading to more effective learning. Recommender systems. Graph-based learning can be used to build recommender systems by capturing user-item interactions and recommending similar items based on the relationships between users and items. Drug discovery. In drug discovery, graph-based learning can be used to analyze the relationships between molecules and predict their therapeutic potential. Graph-based learning. Label propagation utilizes graph structures to represent data points and their relationships, propagating labels across the graph. Kernel methods. A class of algorithms that operate by transforming the input data into a higher dimensional feature space using a kernel function. This transformation can make the data more linearly separable, improving the performance of learning algorithms. In label propagation, the kernel function is used to measure similarity between data points, influencing how labels are propagated across the graph. Support vector machines. SVMs. Kernel methods are fundamental to SVMs, allowing them to handle nonlinear data effectively. Image recognition. Kernel methods are used in image recognition tasks to capture complex patterns and features in images, leading to more accurate classifications. Kernel methods. In label propagation, a kernel function is used to measure similarity between data points. Common kernels include k-nearest neighbors KNN and radial basis function RBF. You have a dataset with 1000 instances, but only 100 are labeled. Which of the following semi-supervised learning techniques would be most appropriate for leveraging the unlabeled data to improve classification accuracy? A. K-nearest neighbors KNN. B. Support vector machines SVM. C. Label spreading. D. All of the above. A. K-nearest neighbors KNN. KNN is a classic lazy learning algorithm that can be adapted for semi-supervised learning. In this scenario, KNN would consider both labeled and unlabeled instances during the classification process, leveraging the unlabeled data to make predictions. The KNN algorithm predicts the label of an unlabeled instance based on the majority class of its k-nearest labeled neighbors. True. B. Support vector machines SVM. SVMs are powerful for classification, and they can be extended to semi-supervised settings. One approach involves creating a decision boundary that maximizes the margin between labeled instances while considering unlabeled data as constraints, which helps in improving the classification accuracy. True. See label spreading. Label spreading is specifically designed for semi-supervised learning. It treats the data as a graph, with instances as nodes. The algorithm propagates labels from labeled nodes to unlabeled nodes based on their connections in the graph. This process effectively leverages unlabeled data to improve classification accuracy. True. D. All of the above. All three techniques can be effectively applied in semi-supervised learning scenarios, with each method having its own strengths and weaknesses. KNN, SVM, and label spreading offer diverse approaches to utilize unlabeled data for better classification accuracy. True. D. All of the above. Semi-supervised learning. A machine learning paradigm that involves training a model on a dataset containing both labeled and unlabeled instances. It aims to leverage the unlabeled data to improve the model's performance compared to solely using labeled data. Image recognition. Labeling a vast dataset of images can be time-consuming. Semi-supervised learning can help by using a smaller set of labeled images to train a model and then leveraging the unlabeled images to enhance the model's ability to recognize various objects and scenes. Text classification. Classifying large amounts of text data can be challenging due to the need for manual annotation. Semi-supervised techniques can leverage unlabeled text to improve the accuracy of classifying documents into different categories. Customer segmentation. Identifying patterns in customer behavior requires analyzing customer data. Semi-supervised learning can help by utilizing a smaller set of labeled customer profiles to train a model and then infer the characteristics of unlabeled customers to segment them into different groups. Label spreading. A graph-based semi-supervised learning algorithm that propagates labels from labeled instances to unlabeled instances based on their connections in a graph representation of the data. This iterative process allows the algorithm to leverage the information from unlabeled data to refine the label assignments and improve classification accuracy. Social network analysis. Analyzing relationships and patterns in social networks can benefit from label spreading. The algorithm can propagate labels from known users to unknown users based on their connections, enabling the identification of clusters and communities within the network. Fraud detection. In financial transactions, identifying fraudulent activities requires analyzing a large number of transactions. Label spreading can help by leveraging a smaller set of labeled transactions to train a model and then propagate labels to unlabeled transactions based on their similarities, improving fraud detection accuracy. K-nearest neighbors. KNN. A lazy learning algorithm that classifies an instance based on the majority class of its k-nearest neighbors in the feature space. It can be adapted for semi-supervised learning by considering both labeled and unlabeled instances during the neighbor search. Recommendation systems. Recommending products or content to users often relies on analyzing user preferences. KNN can be used in semi-supervised scenarios to recommend items based on the preferences of similar users, even if some user data is unlabeled. Support vector machines. SVM. A powerful algorithm for classification that seeks to find an optimal decision boundary that maximizes the margin between labeled instances. SVMs can be extended to handle semi-supervised scenarios by incorporating unlabeled data as constraints during the optimization process, leading to better generalization and improved classification performance. Spam filtering. Identifying spam emails requires classifying messages as spam or legitimate. SVMs can be used in semi-supervised settings to improve spam filtering accuracy by leveraging unlabeled emails as additional constraints in the training process. Image classification. Classifying images into different categories can be challenging due to the complexity and variability of visual data. SVMs can be extended to handle semi-supervised scenarios by utilizing a smaller set of labeled images and a larger set of unlabeled images to learn robust decision boundaries. Graph-based methods. A family of semi-supervised learning techniques that represent the data as a graph, where instances are nodes and connections between them represent relationships or similarities. These methods leverage the graph structure to propagate information from labeled nodes to unlabeled nodes, effectively utilizing the unlabeled data to improve classification or clustering performance. Social network analysis. Understanding the structure and dynamics of social networks requires analyzing the relationships between users. Graph-based methods can leverage the network structure to identify influential users, predict future connections, or detect communities within the network. Recommendation systems. Recommending items to users often relies on analyzing user preferences and connections between items. Graph-based methods can leverage this information to create personalized recommendations by propagating information about user preferences and item connections through the graph. Unlabeled data. Data instances that lack explicit labels or classifications. This data can be valuable for improving the performance of machine learning models, especially in semi-supervised learning scenarios where it can be used to complement labeled data and improve model generalization. Image recognition. A large dataset of unlabeled images can be used to enhance the training of image recognition models, allowing the model to learn more robust features and improve its ability to recognize different objects and scenes. Text classification. Unlabeled text data can be used to improve the accuracy of text classification models by providing additional context and information that can be used to refine the model's decision boundaries. Customer segmentation. Unlabeled customer data can be valuable for improving customer segmentation models by providing insights into the characteristics and behaviors of different customer groups. Classification accuracy. A measure of how well a machine learning model is able to correctly predict the class labels of unseen data. It is a key performance metric in classification tasks, and it can be influenced by factors such as the quality of the data, the choice of algorithm, and the hyperparameter settings. Spam filtering. Classification accuracy is crucial for spam filtering models, as they need to correctly identify spam emails to prevent them from reaching users' inboxes. Image recognition. High classification accuracy is essential for image recognition models, as they need to correctly identify objects and scenes in images for various applications, such as self-driving cars or medical diagnostics. Customer segmentation. Accurate classification of customers into different segments allows businesses to tailor their marketing and sales strategies for each segment, leading to improved customer engagement and satisfaction. From sklearn. Semi-supervised import label spreading. From sklearn. Datasets import make moons. From sklearn. Model selection import train-test split. Import numpy as np. X, Y make moons samples 1000, noise 0.1, random state 42. Strain, stist, a train, a test train test split X, Y, test size 0.2, random state 42. N labeled 100. Indices np.random.choiceLn strain, N labeled, replace false. A train indices -1 assign -1 to unlabeled instances. Label spreading connect, alpha 0.2. Label spread.fit strain, a train. Epard label spread.predict stist. This code snippet demonstrates how to use the label spreading class from sklearn to implement label spreading. It first generates a synthetic dataset using makemoons and then splits the data into training and testing sets. It then labels a subset of the training data and assigns -1 to the remaining unlabeled instances. The label spreading object is initialized with a KNN kernel and an alpha value of 0.2. It is then trained on the labeled and unlabeled training data. Finally, the trained model is used to predict labels for the test data. Which of the following scenarios would benefit the most from using a self-training classifier in scikit-learn? A task with high-quality labeled data where minimal additional effort is needed. B. A problem where obtaining labeled data is expensive, but a large amount of unlabeled data is readily available. C. A scenario where the dataset is extremely small and acquiring more labeled data is not feasible. D. A situation where the data is highly imbalanced, with many examples of one class and very few of another. E. All of the above. False. Self-training classifier is primarily used when labeled data is scarce, making it less beneficial in scenarios with high-quality labeled data. True. Self-training classifier excels in situations where labeled data is costly, but ample unlabeled data exists. It leverages this unlabeled data to improve model performance. True. When labeled data is limited, self-training classifier can be used to effectively expand the training set by incorporating unlabeled data. True. Self-training classifier can help address imbalanced data sets by utilizing the abundant data from the majority class to better classify instances from the minority class. True. Self-training classifier effectively tackles all the mentioned scenarios, making it a valuable tool for diverse data situations. E. All of the above. A learning paradigm where the model is trained on a combination of labeled and unlabeled data. In image classification, using a limited set of labeled images and a large set of unlabeled images for training. This approach can be effective in scenarios where obtaining labels for all images is expensive or time-consuming. Imagine training a model to identify different types of flowers. We have a small set of images labeled with flower names, but we have a large dataset of unlabeled images. We can use semi-supervised learning to train a model that can classify the unlabeled images. A type of semi-supervised learning where the model iteratively trains on unlabeled data that it has predicted with high confidence. In text classification, using a small set of labeled documents and a large corpus of unlabeled text for training. The model can learn from the unlabeled text by identifying instances where it is highly confident about the classification. A scikit-learn estimator that implements self-training. In fraud detection, training a model with a limited set of labeled fraudulent transactions and a large set of unlabeled transactions. The model can learn from the unlabeled data by identifying patterns that indicate fraudulent activity.